Hi friends, welcome to my channel. Let's have a look at today's daily challenge problem, 1020, number of enclaves. In this video, we're going to share and explain two solutions. One is based on traversal, and the other is based on union find. First, I'll read through the problem statement to digest the requirement, and then we explain our plan, and finally, we share the codes and explain them line by line. First, let's look at the problem statement. So here we are given a grid where 0 represents a C cell and 1 represents a land cell. Here, a move consists of walking from one land cell to another adjacent one, also land cell, or working off the boundary of the grid. So we are required to return the number of land cells in the grid for which we cannot walk off the boundary of the grid in any number of moves. Here are two examples, and in the first one, the return is 3. The 3 actually is a counting of the pink ones. The one in yellow actually is in the boundary, right? We can walk off the grid. In the second example, the output is 0 because there are two ones in the boundary and the other two ones are connected with them, right? So we return 0. The constraints for this problem are the following. First, the number of rows and columns are given by m and n. They are in between 1 and 500. And the grid is a binary grid. The elements is either 0 or 1 in integer format. So that's the main problem statement and the examples and additional assumptions. So now let's look at our plan. So here we are going to explain the two solutions based on multi-source depth first search and the union find. So for the multi-source and depth first search, the sources are actually the coordinates that are in the boundary and with value 1 in the grid. So for this method, during the traversal, we could flush the neighboring ones to be 0, and then compute the sum of all elements in the grid. Or we could just count the ones we met during the traversal and use the total number of ones minus the counting. So this is for the first treatment. For the second treatment, we're going to demonstrate the use of union find method again. We're going to put all boundary ones and those ones reachable to the boundary ones to a special cluster. And then we just use the total number of ones minus the proper number of ones in the cluster. So here by proper we mean that we exclude the pseudo coordinate mn we used for convenience, right? With that said, now let's look at the coding. I'm going to first write and explain the multi-source depth first solution. So for this, let me first get the number of rows and number of columns. So this is just for preparation. So next, we're going to get the sources. Let's see. Here, I'm going to initialize a list. So S, I will use it as a stack. And then we're going to iterate, right? For I in, let's see, for J in range N. I'm going to look at the top row and the bottom row, right? So we're going to check if grid 0 J is 1, or just like keep it like this. And then we're going to append this one, this 0G. And also we are going to check the bottom one, that is grid M minus 1G, right? If it's 1, we're going to append this. This is M minus 1, then G. This finishes the check for the top row and bottom row. Now let's look at the left column and the right column. So for I in range, because the 4 corners are already checked, so we're going to start from 1 up to m minus 1 here, right? Because here it will be ending at m minus 2, right, due to the range convention. And then what we're going to check is for if grid. So we're going to check this one. So if we put 0 here, it's the first column, right? Then we're going to append this. So this is I0, right? And then also we check if grade I. So I'm going to write n minus 1. So this is the last column. Then we're going to append that I n minus 1. So this up to now we finished get the sausage. In other words, the coordinates for ones in the boundary. Next, we are going to do the depth first search, right? So this is the basic for loop. So let's use a set to aid the traversal. The role of the set is to avoid repetition. So next, let's do the while loop, while stack. Then first, let me get the position, that is spop, right? And then we're going to do the flushing. So we're going to set this to be 0. Right? Let me make a comment. This is flushing, right? And then what we're going to do, we add visited. We add this coordinate to the visited, meaning that currently we are visiting this coordinate, and in the future this will be already visited. And then we're going to examine the neighbors. So for x, y in the 4 directions, that is r minus 1, c, r plus 1, c, and r c minus 1, r c plus 1, right? Then we want to check if this coordinate is inbound and not visited yet and is corresponding to a 1. So we're going to check if 0 less than or equal to x less than m, and 0 less than or equal to y less than m. And we want to check this xy not in visited. And also we need another condition or check, that is grade xy equals 1. Let's write like this, right? And then what we're going to do is to add this one to the. So we need to add a tuple. This way, basically, after we exit this while loop, we are going to finish the traversal and also the flushing. And then we are ready to do the return, right? We just need to return the current ones in the grid. So this is just a compute some sum, right? Sum array for array in grid. Yeah, this short code actually forms a solution format to this problem. So now let's first do a check. Yeah, it passes one special case. Now let's look at generic case. Yeah, it passes all the generic cases. So with that done, let's move to the second solution. So here I'm going to copy this part. Then I change the class name to be v1. We focus on this one. So this will be based on unified or disjoint set. Disjoint set ADT. So here in the last video, so we implement the DSU as functions, or we implement the unified methods within this solution function. So here, actually, I'm going to take another way. So we are going to implement a unified class or disjoint set abstract data type. So these are the two typical ways of using DSU. One is using within this function, and the other is to regard it as a data structure and implement a class. So in this video, in order to explain or to be different, slightly different than the previous video, I'm going to implement a class DSU out of this class or parallel to this class, and then we instantiate a instance of this guy, and then do the proper logic. So with that said, let's implement this first. So here, typically, if we do this initialization, we're going to do something like this: self root, so originally empty, self rec, originally empty. But in order to treat the ones in the boundary here, I'm going to put the number of rows and the number of columns. So I want to use some pseudo nodes or coordinates. So I'm going to write this as its parent or root, and then I'm going to assign it with a large number of rec. The reason is the consideration is the following. We're going to use this one as a delegate of the ones in the boundary and the ones connected to the ones in the boundary. And also we are going to use union by rank. So because the total number of cells is m by m in this problem. So here we are assign it a large number at m times m plus 1. This is for sure sufficient. So this way of initialization actually is taking account of the problem logic. So this also meant to demonstrate how flexible it can be when we have more control or a good understanding about the problem, right? So this is the one. And next, what we are going to do, we are going to implement the find method. So we're going to accept a formal variable or argument. So here k can be a tuple, right, in this problem. Then what we are going to do, if k not in self root, then we're going to do this: self root k equals itself, and self rec of this k should be set it to be 1. Then we're going to return itself. Otherwise, let's maybe okay. So let's write like yeah. Anyway, so we are going to set result equals self root k, right? Then we'll do a while loop. While result does not equal to self root result. If this is the case, basically what we are going to do, we're going to set result to be its root. In other words, we retrieve up, and then we're going to return the result. If we exit this while loop, result and the root of result will be the same, right? So this is typically the one. Now I'll also copy this line and add one line here. So this actually is path compression. We apply self root in both sides. So let's first put this here, and later we comment that. This is the find solution, find method. Now let's look at the union method. So I'm going to have two coordinates or two arguments, formal arguments, and then let's first find R1 and R2, the roots. Self find K1, self find K2, and then if R1 and R2 were the same, then we do nothing. Otherwise, we check the rec. If self rec of R1 is no less than that of R2, then we're going to set the root of R2 to be R1, and then increment the rec of R1 by that of R2. So we're going to do this. And otherwise, so we're going to do the same thing, but we reverse the direction. So we're going to set the root of R1 to be R2, and then we increment the rec of R2 by that of R1. So that's basically the the union method. So for this problem, I would also like to write another utility function called get clusters. So basically, this accepts no extra argument. So what we're going to do, let's see, we have collections default dictionary. So we're going to use a set as a container. Then we are going to iterate for kv in self root items, but the root self root is a dictionary. Then first we get the root. So let's see, root is self find. We find the root of the current root for v, and then we are going to do d of root at the coordinates k, right? Then we return d. So this way we can see the clusters. So this way we finished implementing the data structure. So we take a relatively a longer way. However, once we know or have a good understanding about this data structure, so we have a lot of freedom. Like here, we take into consideration of the problem logic, and here we write formally, right? And this is also for this problem. So now we are ready to write the problem logic here. So I'm going to copy this one. We get the m and n. And then what I'm going to do is we instantiate a DSU instance. So we pass m and n, right? And then also we want to have a count, or the total count is the total number of ones, right? And then what we are going to do is to traverse, right, for of loop for j in range m, right? And then what we're going to do is to check if grade ij is 1. So I just like this. And then if this is the case, we're going to increment the count by 1. And also, so we want to check if I in this set 0, m minus 1, or j in this set 0, m minus 1. If this is the case, so we're going to do union. We union this with this coordinate mm, so here ij, right? And then we're going to check the neighbors is parallel to the first solution. What we're going to do is we check if I minus 1 is greater than or equal to 0 and grade I minus 1 j, right? If this is 1, so we do DSU union. DSU union. So because I minus 1 and j is first traversed, so let's write I minus 1j, right? So we union with ij. This is 1. So now let's check I plus 1. If this is less than m and grade I plus 1 j, then we're going to do DSU union. So we're going to do ij, right? And I plus 1 j. So actually the order is not essential, but we put the ones first appeared during the for loop. And then let's check for j. So j minus 1, if this is greater than 0, and grade I j minus 1 is also 1. So we're going to do union. Union. So we're going to have I j minus 1 ij. Now we check j plus 1 if it's less than m and grade I j plus 1 if this is 1. So DSU and do union. So we're going to do ij and ij plus 1. Let's do a check. So here we are essentially we do not need this things here, but let's keep this format because we have it already in this if, right? So now we are checking I minus 1j and I plus 1j. Here ij minus 1, here ij plus 1. Okay. So afterwards, so we are ready to write the problem logic. So first, I'm going to call DSU get clusters. So I'm going to this is the function call, right? Then I'm going to get this corresponding cluster, right? Then I compute the length of this set. So because I know this key is already inside, because it's a pseudo key, I'm going to minus this one. So this is the number of zeros that can off the boundary, right? And then what we're going to do is to return the total number of not zero, but ones, because one is land. So this is the ones in the boundary and can be connected to the boundary. So this count is the total number of ones. So we do this difference. This code forms a solution format, right? So now let's first do a check. Yeah, it passes all the one case. Now let's look at generic case. Yeah, it passes all the cases. But when we write here, so we didn't put the path compression here. Let's see if I can put this one. Yeah, it passes. All right. So now let's look at. Yeah, it passes all the cases. With that done, basically that's about it for this video. Let's give a quick summary. In this video, we explained two solutions. One is based on multi-source depth first search, and one is based on unified, right? So here, these two methods are basically in parallel, and I want to say one more thing about the DSU solution. So here, once we understand the problem, actually we have a lot of freedom and a lot of control on how we write the code. So this is one way of writing the solution using DSU. And so basically here, like checking the neighbors are in parallel with the loop here, right? So with that said, I guess that's about it for this video. Thank you.